So can we start? Hello. Hello. Good morning.
Yes,
Good
Doc.
Morning, Doc. Yes,
morning.
Doc.
Yes, Doc.
Yes, Doc.
Okay.
Doc.
I'm happy. Okay. This is how we are going to do it this morning. I'm happy that I was able to catch on what happened in the correlate of Dr. Pipito. So I'm going to show you my slide, but I would like somebody in the class. So anyone who would like to talk about the slide, I will listen in and, because there are actually some part of the slides that are not found in Harper, but in Devlin. So I presume most of you read only Harper. So for those part that you have not read from Harper, I will elaborate on them. Okay. So we will start. Okay. So my topic this morning is only up to peptides for the exam tomorrow. So first of all, can anybody tell me what is the difference between a common amino acid and derived amino acid? Anybody? I can only see three faces, two faces of the student. It would be unfair if I will call their name or three now. Okay, anyone? What is the keyword for you to remember common amino acid, and what is the keyword for you to remember derived amino acid?
Hello, Doc. I can explain for the common amino acid and derived amino acid. So this for common amino acids, the known term or the clue would be the 20 amino acids that can be found in humans, wherein the list in the table for Harper's like valine, glycine, and so on. There are the common amino acids. Well, for the derived amino acids, these are amino acids that are during the post-translational stage na doc, wherein it became mas more into they have a post-translational process from the common amino acid doc. So that is with the
you did not explain very well the common amino acid. It is true the common amino acid are the 20 amino acid that is in the book, but we already have a 21st amino acid, which is
Selenocysteine.
Okay, very good. The selenocysteine. So the common amino acid, these are the amino acid that is found in the genetic dictionary, meaning to say each of them may have one or more than one codon or your triplet nucleotide in the dictionary of the genetic code. Clear? So the keyword there is they have a triplet codon, one or more triplet codon. While the derived is the amino acid that are now found either in peptide or in protein, which we call the amino acid residue. Okay, so these are now amino acid residue found in protein that after translation, they undergo some transformation. So the keyword here is post-translational modification. And as such, the amino acid becomes something else, and it will give the mature protein specific structure, as well as it will improve on each function. Clear? Okay.
Yes, Doc.
So let's go on to that one. So specific codon on the genetic code. Then selenocysteine is the 21st. And these are the derived amino acid. Okay, post-translational modification of the amino acid in peptides or protein. So these are the good example. We have 4-hydroxyproline, 5-hydroxylysine found in collagen. phosphoserine, it is found in glycogen phosphorylase of an enzyme. Most of the enzymes, though they are protein in nature, is correct, but when we ask all enzymes in the mammalian body system is catalyzed by protein enzyme, that is wrong because we have what we call ribozyme. So these are RNA that acts as enzyme, okay, and they play an important part in molecular processes of replication, transcription, or translation. Another one is your gamma carboxyglutamate. So how many carboxyl group do you have in glutamate? How many? You have alpha, right? So there is, okay. So, okay, we will encounter this when we go to the different type of amino acids. So we have the gamma carboxyglutamate. These are particularly found in vitamin K dependent clotting factors. So there is an additional third carboxyl group in the R chain or R group that will provide negativity for the clotting factor to be more efficient. Okay, because it will interact with your calcium, which is also a clotting factor. Okay. So this is very important that all peptides and polypeptides or in protein are polymers of L-alpha amino acid. Okay. We have also other amino acids found in the body free in circulation in the blood, exemplified by your glutamine or alanine. Okay. Then there is what we call the combined state. They are not associated with peptides or with protein, but by itself, it combined with other amino acid to perform the specialized product derived from amino acids. So example of this is your creatine or hemoglobin or the heme. Okay. So other functions of amino acid is that they can be converted, okay, into amines or neurotransmitter. Then they are found definitely in your protein. Example here that was given is your thyroid hormones. So thyroid hormones have tyrosine, and then the tyrosine is actually iodinated for the functions of your thyroid hormones. Then glycine and glutamate by themselves are neurotransmitter. So by these three slides, you will notice that amino acid is very important because it can give rise to different types of protein that can play an important function in the body. Okay. And we have three types of nutrients. The lipid, which is also diverse in its or more complex in its structure. Then we have the carbohydrates, and then we have the protein. And it is only in protein that you eat amino acid in protein that you found the nitrogen atom. Okay. Per se, lipid and carbohydrates do not have the nitrogen atom. That is precisely the point why amino acid can give rise to specialized products. Okay. Anybody who would like to talk about the structure of amino acid, what are we looking at? Anybody?
I'd like to expound on it, Doc.
Okay, very good. Go ahead.
Doc, as you can see in the structure for amino acid, Doc, you have your central carbon, Doc. Then in that central carbon, Doc, you have your amino group, and then which is your NH3. Then you have your carboxylic acid group, which is your C double bond O, then an O, and then your hydrogen atom, and then also your side chain, Doc, which is represented as R.
Okay, so can you talk more about the alpha carbon, which is the central or the tetrahedral carbon? What do you mean by tetrahedral? So there are 4 substitution, right? Okay, you mentioned that already. So what is the meaning of chiral carbon? What are you looking at attached to alpha carbon?
A chiral carbon is
Okay,
it's a carbon that is attached to 4 different groups.
Okay, so 4 different groups, and these groups again are, can we mention it again?
A hydrogen, an amino group, a carboxylic acid group, and a R side chain group.
Okay, how about the handedness? What do we mean by handedness? Anyone?
Handedness, Doc, refers to whether it's a level or left rotation, going structure of the amino acid, or dextro, which is when it goes to the right.
Okay, rotation of the polarized light, either to the left or to the right. So it is levo, which is a small l, and dextro, which is a small d. How about stereoisomerism? Okay, we go back to this slide here. That one, the first bullet. Okay, go ahead.
For stereoisomerism, Doc, as per my understanding, Doc, it is like a form of isomerism in which you have the same number of molecules in the same molecular formula. However,
Yes.
you only differ in the 3-dimensional positioning of the atoms in your structural formula, Doc.
Okay, that is correct. Then what is the meaning of the L, big L, and big D isomers? That is one type of isomerism, big L and big D. That's why I am emphasizing that the big D and the big L isomers is different from the small L and the small D. Okay, dextro-rotatory or levo-rotatory. Okay, so we will go on. That is correct. It is the special 3-dimensional special configuration of the atoms in the structure. So tetrahedral, that is why it is called chiral. Okay. Then chirality will describe the handedness of the molecule by the ability of it to rotate the plane of the polarized light either to the right or to the left. Okay. Then the D and L isomers, all amino acid in protein has an absolute steric configuration, which is the L-alpha amino acid. Okay, so this is all amino acid in the mammalian protein exists as L-alpha amino acid. However, there is the D amino acid that is actually found in nature. And this is exemplified by the amino acid that may be found in your polypeptide antibiotics. Okay. Now, what is our reference molecule when we say L? This is your L-glyceraldehyde. You look at the amino group, it is always on the left side. You understand that? The amino group. Then, okay, what is this saying? Classification, the best way to classify amino acid is how?
On the basis of their R groups, Doc.
And on the basis of their
R groups.
R groups. Okay. What about the R groups?
There are R groups that would identify as hydrophobic and others would identify as hydrophilic, meaning some are polar uncharged amino acids and other are charged amino acids, Doc.
Okay, meaning to say all amino acid have alpha amino group and alpha carboxylate group, right? Then they differ on the R group, and precisely they can be differentiated by the R groups. And the best way to classify them is to look at the R group, whether it is hydrophobic, does not like water, or hydrophilic. And if it is hydrophobic, what do you think would be the R group structural or chemical nature? This is organic chem. Anyone?
Aliphatic, Doc.
Very good. Good. So aliphatic, what else?
Aromatic, Doc.
Okay, so aliphatic and aromatic group. Hydrophilic, what does it mean? Loving water. Why is it polar uncharged and charged amino acid? Why do you think? What is the structure of your water? A very simple molecule. It is partially positive and partially negative, is it not? When you look at the water, it is partially positive and partially negative. That's why any polar group, we need to say if there is hydrogen bonding because of the polarity of the amino acid, but it is not charged, then it can be hydrophilic. And can anyone give me an example? I said hydrogen bonds should appear here, whether it is a hydrogen donor or a hydrogen acceptor. Maybe the charge positive and the charge negative. Anyone who can give me the charge positive and negative? There are how many positive and how many negative amino acid?
For the positive, Doc, there are 3, which is lysine, histidine, and arginine. Then for the negative, there are 2. That would be glutamic and aspartic acid.
Okay, glutamic and aspartic acid. So there is an additional carboxylate group in the R group. Okay, which one is how many? So you have the C at the center, then you have the CH2, and then you have the COO. So this is aspartate or glutamate? Okay, let's go on. I'll let you see the. So L-alanine, which consists a metal R group, an alkyl group is hydrophobic. Serine, which is the CH2OH, it is polar because of the OH. And also, I cannot see. Okay. Aspartate, which is the negative amino acid because there is the COO negative in the R group. So we have the aliphatic or the alkyl R group. Okay. Then you have the aromatic R group. So in the aromatic R group, phenylalanine and then tyrosine, then tryptophan, which of the 3 do you think has the possibility of being a polar?
Tyrosine, Doc?
Yes, tyrosine because of the OH. So depending on the pK of the OH, which can be an ionizable ion, here the H, and the pH of the environment, this can be deionated. Okay, so it will now carry a negative charge. And then take a look at valine, leucine, and isoleucine. What does the R group look like? How does it differ from alanine and methionine? You see branching, right? And these three are referred to as the branch amino acid. Okay? So isoleucine, valine, and leucine are your branch amino acid. Then which amino acid has the sulfur atom?
Methionine.
Methionine and
Cysteine.
cysteine. And between the two, which can form a disulfide bond.
Cysteine, Doc.
And what do you call the R group in cysteine? The name of the SH. This is what,
Sulfhydryl, Doc.
okay, thiol group, THIOL, the thiol group, okay? Lysine, what do you have? You have epsilon amino group, alpha, beta, gamma, delta, epsilon, attached to the epsilon carbon. Okay, that is precisely the name. It has an epsilon amino group in the side chains. And then the arginine, this is what we call the guanidinium group. The C double bond N, that is where the positivity is found. And then the histidine is your imidazole group. Okay. There is an amino acid here that is not really an amino acid, but an amino acid. And we are referring to
Proline.
Proline, Doc.
pyrrolidine. Okay, what is the difference in the pyrrolidine to the other amino acid?
The R group connects to the amine group. No?
Okay, so there is a connection between the alpha amino to the R group. Okay, so it will form what we call your pyrrolidine ring. Now, we said that the amino acid can exhibit handedness, whether D or L, and there is an exception. The exception is, you need to say it cannot. Why glycine?
Because lysine is a chiral, no?
Okay, so in the real sense, the alpha carbon of glycine is not truly chiral because you have two proton attached, not just one H, okay? So the R group is just an H. Okay. Okay. Mahang siya kung di malihok dayon. Okay. Okay, there we are. And this is another way of looking at it. Okay, you have the small amino acid, which is glycine, is of course the smallest, followed by alanine. Then we mentioned about the branch chain. We also mentioned about the hydroxyl amino acid. Aside from serine, we have the threonine, then the aromatic, then the acidic, and the derivatives. So the derivatives are referring to the asparagine derived from glutamate and glutamine derived from glutamate. Okay, so what do you see? Instead of a carboxyl group, you have the CONH2. So at this point, the two negative amino acid will give rise to two polar amino acid, which are asparagine and glutamine, without charge, but still polar. I put up on the side a 3-letter designation of the amino acid and a 1-letter designation. I expect you to know the 3-letter designation because it is easier. It will just carry the first 3 letters of the amino acid. Okay, it's kind of difficult to remember the 1 letter because some is more about how it sounds. The reason why they have given a particular letter as a one-letter designation. So the expectation is for you to know the three-letter amino acid. Okay. Now let's take a look at selenocysteine. It differs from cysteine by replacing the sulfur atom to a selenium atom. And the three-letter is SEC, that is selenocysteine. Se for selenium and C for cysteine. Why it is called a 21st amino acid? Because if you are going to read through the presentation or the PowerPoint, it says here that this is not a post-translational modification process, but the change happened during translation. You get it? We will have more of this when we go to translation of protein, okay? So it will actually create an unusual tRNA that will recognize something in the mRNA that will allow it to put in the selenium cysteine, okay? So these are example of your cysteine containing protein. They act as peroxidases or reductases. Example, thioredoxin reductase. I want you to remember this because this is part of the knowledge that you have to remember when we move on to nucleotide metabolism. Okay, nucleotide metabolism. Glutathione peroxidase is important when we talk about the hemoglobin structure. And the iodinase is important when we talk about the synthesis of T3 and T4 in the thyroid glands. Okay. Now, it has been noted that impairment of the selenoprotein can give rise to certain clinical conditions, such as it can give rise to tumor formation. It did not specify because this is what is only noted in the book, whether this tumor can be cancerous or not. But alarming would be atherosclerosis in the blood vessel wall, which will lead to a lot of abnormality or dysfunction involving your big as well as small blood vessels, and a specific selenium deficiency cardiomyopathy known as Hisham disease. Okay, so what is important here is selenocysteine is not classified as a derived amino acid because it is not post-translational modification, but the modification happened while translation is happening. That's one. And then, but they are particularly important, acting as peroxidases or reductases enzymes in the body. And then it can also lead to clinical conditions. Oh my God. Okay. So anyone who would like to talk about, in this particular, the following discussion would actually be telling you why it is at pH 7.4 of the body, the amino acid per se exists as alpha carboxylate group, meaning to say it carry a negative charge, and the amino group is the ammonium or the amino group which carry a positive charge. And this has something to do with the ionizable group found in these two parts of the amino acid structure, the alpha amino and the alpha carboxyl group, as well as the acidic or basic group. So it is about the pK value of the ionizable group and the pH of the existing environment. So, okay, so important is we have the ionizable group, okay, in the alpha and the alpha amino and carboxyl group, as well as in the acidic and basic group. Then, as mentioned, it depends on what we call the pK value. So if you look, so anybody who can tell us, aside from the importance of knowing the association between the pK value and the pH environment, which will tell us what is the structural characteristic in the body of amino acid, as well as there is another function of this knowledge also. So it says here that the carboxyl group has a pK of 2 to 3, and the amino group has a pK of 9 to 10, and the pH of your body environment is 7.4. So how can you make a general statement looking at these two, the lower bullet? Anyone? Meaning to say, if the value of the pK is belong to the pH of the environment, what will happen?
Doc, I'll just try. So for if the pH is less than the pK, it will exhibit a positive charge. And then if the pH is greater than the pK, then it will exhibit a negative charge.
Okay, that is also correct. But personally, it would be easier for me if I look at the pK, then I talk about the pH. So if that is the case, so meaning to say the carboxylate group, okay, we will go on, that's correct. Then, okay, you have a formula that you see in the book wherein it is NH2, alpha NH2, then COO negative, and then the H, and then the R group. This structural formula, can somebody try to understand this formula, whether this is possible or not? In any pH environment. Are you getting the point? It says that if the pH of the environment is greater than the pK of the amino acid, so the pK can either be the alpha pK1 alpha carboxylic group, or the pK2 the alpha amino group, and the R is the pK3. Okay. So can you say it again? The one who mentioned about the relationship between the pH and the pK.
Yes, Doc.
Okay.
If the pH is less than the pK, it will exhibit a positive charge. And then if the pH is greater than the pK, it will exhibit a negative charge.
I think it would be better to say if the pH is greater than the pK, that is the one that you said, it will be protonated. And if it is less than, wait, because I remember about pK. If the pK is less than the pH, then it is unprotonated. If the pK is more than the pH, then it is protonated. Okay, because when you say it is protonated, it will either have a positive group or it does not have a negative group, because of the pK value. Okay, the following slide would be clearer. But first of all, we have these two terms to remember. Sweeter ion means there is no net charge, or the amino acid is neutral. The positive and the negative cancel out each other, so it becomes neutral. And it is called a sweeter ion. And what is the isoelectric point, or the PI? The PI is the pH wherein the sweeter ion exists. So meaning to say, wherein the amino acid is neutral. Okay? So sweeter ion and PI. Now, knowing all of this has something to do with separating the amino acid or the protein, depending on the PI value. Okay. Do we need to explain this? This is in the book. Actually, were you able to appreciate what the book is telling you? Okay, the first one is relatively easy. So this is about alanine, okay? So the pK of the alpha carboxyl is 2.3. That's why they are protonated. The amino group has the H, also the COO has the H, because the pK of the alpha carboxylate is 2.3 and the pH is lower, so they are protonated. But as you keep on adding a base, so it will increase the pH of the environment, okay? To such point, when the pH of the environment is now 6.1, the alpha carboxylic group will now lose the proton, so it becomes negatively charged, okay? And then you keep on adding to such point wherein the pH is now very basic, that it can now lose the proton of your alpha amino group, which has a pK of 9.1. So if you are going to look at the acidic end, most likely the amino acid are positively charged. But towards the basic end, then the amino acid will be negatively charged. Are you following? And then you try to take a look at where is the sweeter ion. In this particular example, it is the pH, which is 6.1. So that pH is now known as the PI, or the isoelectric point of alanine. That is very easy. If this is a hydrophobic amino acid, you only have 2 protonated group. How about when you have the next example? This is now what? Aspartic acid. Okay, so the same. We follow the pK and the pH of the environment. So the first proton that is released is the alpha carboxylic group, and then the next pH 6.95, wherein the pK of the beta in the R group, carboxyl group, is 3.9. So this time it will also lose its proton. So this is now wherein you have a negative molecule. And then as you add more base, it will now act on the alpha amino group, will also now be losing its proton. So in the basic environment, it becomes more negative, while at the beginning, in the acidic environment, it is positive. Are you getting it? This time, how do you compute for the PI? So you look at where the sweeter ion is found. The sweeter ion is found in pH 6.9. So you will take the pK of your beta carboxyl group and the pK of your alpha amino group divided by 2. So any question about this? Okay. So this is a table again that I picked up from Harper. As you will notice, lowest pK is found in alpha carboxyl group, followed by the R group. Okay, and take a look at imidazole. It ranges between 6.5 and 7.4. So what is that telling us? It is telling us that the pK of the imidazole histidine is very near the pH, so it can act as an acid and it can act as a base. So it is a good buffer. Get it? And I mentioned about the SH of cysteine, the OH of tyrosine, okay, which can also carry a negative charge depending now on the pH of the environment, because they can be deprotonated, so the H will be released. Then the alpha amino group is 8 to 9, followed by epsilon amino group of lysine and guanidinium group of arginine, which has the highest pK value. Okay. So the net charge of any amino acid, peptides, or protein will depend upon the pH of the surrounding aqueous environment. But if you look at the amino acid, the positive and the negative end will become zero, right? The alpha amino group and the alpha carboxylate group, it will become zero. And the peptide and the protein will start with the N terminus and with the carboxyl terminus. So they will also cancel each other out. So in the examination, if I decided to give you a molecule wherein I will write the amino acid sequence, then the decision is to see how many positive or how many negative amino acid are grouped. Will give you the charge of that particular protein or peptide. Right? Is that clear? Because the N positive and the C N terminus, which is positive, and the C terminus, which is negative, will cancel each other out. So we will be looking only at the R group, whether it has a positive or a negative. We are always saying the environment in the body, which is 7.4. Okay? That is why they will carry a negative charge or a positive charge, aspartate and glutamate, and positive histidine, lysine, and asparagine. Okay. Because of the charge group on the amino acid, it is soluble in polar solvents. Okay. And it has a high melting points because you need high energy to disrupt the ionic forces, meaning to say the positive and the negative that stabilize the crystal lattice. That will happen in amino acid mixtures. So the 20L alpha amino acid in solution, the nature of the amino acid R group is very important because it has the ability to interact non-covalently with each other or with another molecule in the system. And of course, you have the covalent group, covalent bond here referring to the disulfide and the peptide bonds, okay? That will dictate the structure and function relationship of the peptide and proteins. So you now understand that the structure will dictate what will, the amino acid R group is the one that will dictate what is the structure of that particular peptide or proteins as well as the function. So hydrophilic is found in the exterior of the protein because it can interact with water. I mean, the hydrophobic is, found in the center. So if this is an enzyme, if it is found in the active site of the enzyme and it is found in the interior, then it plays an important part in the function of the enzyme. Here we are, the imidazole wing of the histidine, which has a pK value of 6.5 to 7. Something allow it to act as a proton donor or acceptor at the physiological pH. Again, it can be found in the reactive center of the enzymes, or more importantly, it has the ability to act as a buffer. There is a lot of histidine residues in the hemoglobin structure. And this has something to do also with the transport and exchange of oxygen and carbon dioxide. Now, all of this is in Harper, okay? So the primary alcohol of serine and the thiol group of cysteine can act as a nucleophile. Nucleophile is electron rich or electron poor.
Electron.
Electron rich. Electrophile is looking for or loving for electrons. So electrophile is electron poor, while the neutrophil is electron rich. Okay. Then I mentioned about the thiol group of cysteine coming together to form your disulfide bond. I also mentioned already about the OH of serine and threonine to form hydrogen bonding. Okay. Then covalent bond can happen with your carbohydrates to form your glycoprotein, or with your phosphate to form your phosphoprotein. Then the OH of your tyrosine is the one that will bind to the phosphate group. You will learn later on that the addition of phosphate group or the phosphoprotein can act as an enzyme or can act as other function already because of the added phosphate group. Okay. I think everybody is found or looking at CSI when they try to look and find out if there is blood stain in the environment. If it glows, so it is the aromatic R group, but more importantly, it is referring to your tryptophan at 2080 nm wavelength of the ultraviolet light. Okay. We mentioned this already. Then, okay. When we talk about the structure of the protein, as you have seen in the first slide, you see something bending, and then you see some coil or all of that. So in the structure of protein, there are actually 4: primary, secondary, tertiary, quaternary, and some book will even mention quaternary protein. That is basing on the structure as well as on the number of polypeptide chain found in that protein. Now, glycine and alanine being the small and the smallest amino acid can occupy little space, and this is usually found when 2 polypeptide comes together, and they will, they can bend, and the direction of the polypeptide will be either to the same side or to the opposite side. So it has something to do with structure of the protein. Likewise with proline, so it is often found at the bend of the polypeptide, these 3 amino acids. And these are the reaction. Peptide bond formation is between the amino acyl group and the carboxyl group. The carboxyl group to the amino acyl group, because it starts with the N terminus. So the one is the carboxyl group is free. It interacts with the next amino group down the line. Then transamination, just remember that shift-base formation is happening there in the reactions. Another important knowledge is you need your B6 amino acid acting as a coenzyme pyridoxal phosphate. Then decarboxylation will lead to amino acid amine, and reaction with ninhydrin and fluoriscamine is to detect the presence of protein. Okay. between the two, it is fluoresceamine that is actually more sensitive. So with ninhydrin, the reaction is referred to as oxidative decarboxylation. All of the amino acid, not all, most amino acid will give you the Roman purple at 570 nm. Since proline is in reality an amino acid, so it will give rise to a different color compound, which is now yellow. Okay. Fluoresceamine is a non-fluorescent compound actually that will react with the primary amines, then it will become a fluorescent product. So its sensitivity is 10 to 100 times better than the amino acid mixture react or the protein reacting with your ninhydrin. So remember, with the use of ninhydrin, the reaction involved is oxidative decarboxylation. And then the other one is it will colloid. It will not colloid, it will give light. Okay. So this is an example of shift base. Never mind the reaction. Then decarboxylation, I have given you two examples, and take note again of the role of pyridoxal phosphate. So that is the shortcut, PLP, pyridoxal phosphate. In examination, I will use like this. I'm not going to write the whole word. So PLP is pyridoxal phosphate. It is needed in the decarboxylation of glutamate, and the enzyme is glutamate decarboxylase. Okay, and the product is gamma aminobutyric acid, GABA, which is a neurotransmitter. On the other hand, if we have histidine, you have your histidine decarboxylase. Again, in the presence of pyridoxal phosphate, you remove the carbon dioxide, it will give rise to your histamine, which is a mediator for allergic reaction. Now, this is now the most important, of course, reaction of amino acid to be able to form peptides or protein. So what will happen? The condensation is between you look at the green color, carboxyl, alpha carboxyl, and the next alpha amino group. So there is the release of water, H2O will be released. And then you now have the peptide bond. So this is condensation with elimination of water. Because of the presence of resonance hybrid of the two structures, this gives rise to an important property of the peptide bond. It is a strong bond because it gives a partial double bond character, and it becomes relatively rigid around the peptide bond. So it will inhibit the rotation. So the protein molecule in its primary structure is quite stable. So obviously, primary structure refers to just the sequence of amino acid in a polypeptide chain. So what are the sequence? Now, another important property is the 4 atoms bound to the carbonyl carbon and the amide nitrogen. They form a plane and they are said to be coplanar. Okay. Then trans configuration, was this mentioned by Dr. Pipito? When you are on the topic of the membrane, the difference between cis and trans configuration in the presence of a double bond. When you say trans, they are opposite. The atoms are opposite each other. You look at the CO, they are opposite each other. That is the meaning of trans configuration. Okay, paper from ion exchange and electrophoresis. So this is paper chromatography. We used to have a laboratory work on this, wherein the student, as the faculty, I will be the one to put on